Hi there. In today's lecture, we're going to be starting a new application of differentiation, and that is rate of change. So rate of change is used quite a lot in physics, engineering, chemistry, and so on. Whenever we have something that is changing, that can be changing in space, changing in time, etc. Okay, so let's start off with a very simple example just to illustrate what we're doing, and then we'll look at more complicated examples. Okay, so we start by looking at the position of a particle and then finding the rate of change of position, which will be the velocity, the rate of change of velocity, and so on. Okay, so consider the position x of t of a particle. Okay, so if we have our x line over here, then at some time t, the particle will be at position x of t. Now the rate of change of position, that will be the velocity. Okay, so that's just a recap of high school work. So we know that the average speed, that would be x2 minus x1 over t2 minus t1, or delta x over delta t. If we take the limit as delta t goes to 0, then this average speed becomes the instantaneous speed, or the velocity. Then the deltas change to d, so we have dx by dt. Okay, and this will be our velocity. And then we can repeat this procedure again and then find the rate of change of velocity, and we know from our high school work that this will then be the acceleration. Okay, so let's have a look at some examples. So if we have, for example, a ball falling from rest from a height h. Okay, so we've got this following situation. There's a ball that's falling from some height h. Okay, then we can find its position at any given time. So let's say the position over here is y of t for the height, then y of t will be h minus 1/2 g t squared. Okay, we know g, that's the acceleration due to gravity, so that is the position. If we want to know the velocity, we can write v of t. Sometimes this is written as y dot of t. Okay, we just differentiate the position, and then that gives us the velocity, so that will be minus gt. Okay, and then we can differentiate this again and get the acceleration. So a of t, sometimes written as y double dots t, that will just be minus g. So here we've got the position, the velocity, and the acceleration. Okay, so how are these related graphically? So here, algebraically, we can take the derivative, and then we can see from the position we get the velocity, then we get the acceleration. If we were to sketch the position, can we determine the velocity and the acceleration graphically? Okay, so graphical representation of position, velocity, and acceleration. Okay, so all of this again, this is just a recap of the high school work. Later on we will look at the new material. Okay, so again, if we can draw a graph of this here, so we've got t, y, and then we'll use this example here with this object falling. So it's h minus half gt squared. Let's say maybe it looks something like this. Okay, so it's an upside down parabola just by looking at that formula over there. And then here we have h where it starts. Okay, so if this is the position as a function of time, then the derivative will give us the velocity, but we know that the derivative is also another way of saying the tangent, right? If we take the derivative, that gives us the gradient of the tangent line. So if we draw in a couple of tangent lines, that will show us a graphical representation of the velocity. So we see at the top here, the tangent line is horizontal, so it has 0 gradient. So here, gradient is equal to 0, which makes sense because we said that the particle starts from rest. So that means the gradient or the velocity at that beginning point must be 0, right? Because it started from rest. And then at some other points, let's say over here, we've got another tangent line. Now the tangent line is sloping down. Okay, so it's got a negative gradient. Negative gradient. Okay, and then the negative gradient, that corresponds to a negative velocity because the object is falling downwards instead of going up. So negative velocity. Okay, and then right at the end here, we can again draw in a tangent line, and then this would be the maximum velocity, right? Because at the end here, the tangent line is almost vertical there. So here, this corresponds to a very high velocity. So a very steep gradient means a very high velocity. Steep gradient, high velocity. Okay, and again, it's sloping down, so it's got a negative gradient, which means the velocity is negative because it's falling down. So we see from these three snapshots in time, so number 1, number 2, and number 3, we see that the gradient started out being 0, so it was just a horizontal tangent line, which meant that the initial velocity was 0. Then at moment number 2, we've got a negative gradient, so it's a negative velocity, so that the object is falling down. And then number 3, it's a very steep gradient. Again, it's negative, so that means it's a high velocity, again, falling down. Okay, so given the position as a function of time, we can use the gradient to determine the sign of the velocity. So is it sloping down? Is it sloping up? That tells you if the velocity is positive or negative. And the degree of the slope, that tells us how large the velocity is. So if the slope is 0, so horizontal line, that's 0 velocity. If it's very steep, that means it's very high velocity. Okay, and we can do the same sort of thing with a velocity versus time graph, and we can use that to determine the acceleration. So let's have a look again with this example. So now let's draw in a velocity versus time, and we'll use the same example we have here. So here, v of t, that is minus gt. So we have a straight line, and it's negative. So we can draw it like this. Okay. So it's a negative velocity, we know it's moving down, and since it's a straight line, it has constant gradient, constant negative gradient. Okay, so that means constant negative acceleration. Okay, because at some point here, we draw on the tangent line, we see that it's a negative tangent line sloping down, So we have negative acceleration. So this will be constant negative acceleration. Okay. And that's just from this example here. So since we have this object falling, the velocity will have this form, and so we'll have a constant negative acceleration. However, for a different case, so maybe for another example, we might have something like this. The velocity versus time. Maybe it's not constant, maybe it looks something like this. Okay, and again, we want to determine the acceleration. So to determine the acceleration at any point, we can draw in a tangent line. So let's say at the beginning here, we've got this tangent line. Okay, so we see that it's sloping up. Okay, it's fairly steep. So we see we have positive acceleration. Positive acceleration. Okay, and we can see from the rest of the picture, if we move right, we see the velocity increases. So a positive acceleration means that the velocity increases, which is what we expect. Okay, and then at this other point here, we see that we have a horizontal tangent line, so this means no acceleration. Okay, so there's no acceleration at this point. So the velocity has reached a maximum, we're not going any faster, no acceleration, and then afterwards we see that the tangent lines are actually sloping down now. So here we have negative acceleration. Okay, so negative acceleration, we are now slowing down. So the velocity is still positive because we're in the top portion. Okay, so we're in the positive velocity region. However, the velocity is decreasing. So negative acceleration, velocity is decreasing. Okay, but it's still positive, just decreasing. And then at the bottom here, the last point we're going to be looking at, again, the acceleration is negative, so, no acceleration. So no acceleration, a equals 0. But here the velocity is negative. Okay, so in the previous case where we had no acceleration, the velocity was positive because we're in the top part. Here we're in the bottom negative part. So the velocity is negative and there's no acceleration. In other words, the particle turned around when the velocity started being negative. So from this point onwards, the particle turned around, it moved in the opposite direction. The speed increased in the opposite direction until this point here, where the velocity reached a maximum, again in the opposite direction. So no more acceleration. And then over here, we see that there is, positive acceleration, and so moves the velocity from being negative to being more positive. Okay, so here it's turning around again. Turning around again. Okay, so we can see from the plot what the velocity looks like, so that's just from the graph, and we can also see what the acceleration looks like by looking at the tangent lines. So just in summary, if we are given the position as a function of time, then we can see where the particle is, and then by looking at the tangent lines, we can see what the velocity is. Okay. Then if we are given the velocity as a function of time, then the graph will tell us how fast the particle is, and then the gradients, or the tangent lines, will tell us how much acceleration there is. Okay, so the tangent lines will have different meanings depending on what graph we're looking at. If we're looking at position, then the tangent lines will be velocity. If we're looking at velocity, then the tangent lines will be acceleration. Okay, so please keep in mind what the graph is. The tangent lines will have different meaning depending on what type of graph we have. Okay, so please look at exercise 2.7. This is the tutorial work. Okay, this will cover all of these examples of looking at the graphs and finding the different rates of change. Okay, so the velocity or the acceleration. So that's exercise 2.7, 5 to 10, 14, and 15. Okay, so this will be on the rate of change. Okay, so very similar to what we went through now, looking at the position as a function of time, velocity as a function of time, and the acceleration as a function of time. Okay, so that is the first part of the tutorial. The second part of the tutorial, which we'll be covering now, that will be exercise 2.8, 1 to 8, and then number 13. Okay, and then that will be on related rates of change, which we will start soon. Okay, so related rates of change. Okay, so those are the two exercises for this week's tutorial. Okay, so the solutions will be posted as well. Please go through them to check your work. If you have any issues, please send me an email or you can ask the tutors for help. Okay, so since everything has been moved to online, the tutorials will also be online and they will be done on the tutorial WhatsApp groups. Okay, so previously you were separated into the different groups with the different tutors. So this Thursday you will be asking your questions on the respective WhatsApp groups. Okay, if you have any questions about that or you forgot which group you're in, please just send me an email and then we can sort that out. Okay, but this Thursday, online tutorials. Okay, so let's have a look at the second part of this chapter on related rates of change. Related rates of change. Okay, so instead of looking at the rate of change of a single function, okay, so for example, the rate of change of position, that's velocity, we're only looking at one thing that's changing. For related rates of change, we're looking at the relationship between two things that are changing and how the change in the one affects the change in the other. So as a first example, let's consider a spherical balloon being inflated. Okay. Determine the rate of change of the radius. So that's the first one, rate of change of the radius in terms of the rate of change of the volume. Okay, so we can imagine if we've got a spherical balloon with some radius, let's say this is at t equals 0, then after some time the volume increases because it's being inflated. So now we've got a bigger volume at t equals, let's say t equals 1, and then we might have an even bigger volume at t equals 3. So we know how the volume changes, okay, but we're asking, how does the radius change? So let's say we know how the volume changes. How does the radius change? Okay, so this is what we mean by related rates of change. We know the rates of change of one thing. How does that affect the other thing? So let's start off with what connects the two. So if we know the volume and we want to find how the radius changes, what connects the volume and the radius? Well, that is the formula for the volume of a sphere. So we know that V is going to be 4 over 3 pi r cubed. Now, V and R are not constants in this case. They both depend on time, because as this balloon inflates, the volume is going to change in time as well as the radius. So here, V is actually a function of time, and R is a function of time. So they're not constants. Okay, so let's substitute that and see what we get. So V, that's going to be V of t, since it's a function. We have 4 over 3 pi r, that's going to be r of t cubed. Okay, so that's just so that we know that both of these are functions of time and not just some constants. Now, what we want to do is determine the rate of change of the radius in terms of the rate of change of the volume. So to find the rate of change, we need to do the time derivative on both sides. So we're going to have d by dt v of t is d by dt of all of this, 4 over 3 pi r of t cubed. Okay, so rate of change, that means time derivative. So rate of change, that means time derivative. Okay, so let's take the time derivative on both sides and see what we get. So we end up with dv by dt, which we know, but we want to find dr by dt in terms of this. So here we're going to get 4 pi r of t squared, and chain rule, we've got an inside function and an outside function. The derivative of the inside will be dr by dt. Now what we want is dr by dt. So a little bit of manipulation. We see that dr by dt is equal to dv by dt, and then we need to divide through here. So 1 over 4 pi r squared. So given the radius and given the rate of change of the volume, we can determine the rate of change of the radius. So given the radius and the rate of change of the volume, we can work out the rate of change of the radius. Okay, and then that's just substituting some values, and then we can see what that is. Okay, so this is just a first example of this idea of related rates of change. So we've got one rate of change, this dr by dt. We want to relate it to another rate of change, that's this dv by dt. And this is how they are related to each other through this formula. Okay, let's have a look at another example. Okay, so consider a cone that holds water. Okay, so it's something like this. Okay, and it's got some water. It's got some water in it. Okay, the cone is leaking water at a rate of 1 centimeter cubed per second. Okay, so the water is leaking out of this cone. Maybe we've got a hole here and the water's coming out. So as the water comes out, we know that the water line over there, this level here, that's going to go down. Okay, so this will cause the height of the water to decrease. Right, so the height that will decrease as we go down. Okay, determine the rate of change of the height at height h. Okay, so we've got this cone of water. Water is leaking out at this rate of 1 centimeter cubed per second. Okay, so we know that as the water goes out, the height of the water will decrease. We want to determine the rate of change of this height at some given height. Okay, so let's say when it's halfway, there's some certain rate of change of the height. As the water goes out, does the height decrease quicker? Does it decrease more slowly? We want to determine that. Okay, so how does this height change in time? Okay, so let's start out with the volume of this. So the volume, that's going to be 1/3 pi r squared h. So r, that's the base radius here. So that's r, and this is h. Okay, what we want to do is determine the rate of change of the height. Okay, so how can we do that? So let's start off with a picture. Let's put this as a capital H so we don't confuse things. So we'll put capital R for the space radius and capital H for the height. So it will be pi capital R squared capital H. Okay, so that's just to not confuse this. We can say little r and little h is the radius and the height at some time t. So h and r, that's when it's full. Little h, little r, that's when it's partially full. So here, let's put the water line there. So r and h, lowercase, are the radius and height at some time t. Okay, so now what we want to do is find the relationship between these, because the question asks us about just this h over here, but when we're finding the volume, we need h and r. Okay, so let's just redraw this a bit. So we can see that this triangle here, over there, and over there with this slope of the cone, that's a right angle triangle. So here we've got a triangle. Again, it's right angled. We've got capital R there, little r there. Capital H, that's the full heart. Little h, that's the smaller one there. Okay, and both of these triangles have this common angle. Let's call it theta. So tan theta, if we consider the big triangle, that's going to be opposite over adjacent, so that's capital R over capital H. If we consider the big triangle, if we consider the smaller triangle, that's going to be little r over little h. A little bit of rearranging, we can solve for r. That's going to be little h times capital R over capital H. That's our little r. So we can use this fact to replace the little r in the formula so that we only have it in terms of h. Right, because this formula has the height and the radius, but we're only interested in the height, so we need to eliminate the radius. Okay, so we can write V is equal to 1/3 pi r squared h. So that is the little r and little h, so that's the volume of the water, not the volume of the full cone. But the little r we can eliminate by substituting this equation that we found here. So this is going to be 1/3 pi, and then all of this squared, so h r over h squared times the other little h. So this will be 1/3 pi capital R squared over capital H squared, and then the h squared from the brackets and the other h outside, that will be h cubed. Okay, so now the volume is only dependent on the height. We don't need to worry about what the radius is. Okay, so we've got this new formula without the radius to worry about. Now what we want is to determine the rate of change of the height. Okay, so that's what the question's asking us for. So what we can do is differentiate both sides, because remember, rate of change, that's the time derivative. So we're going to have d by dt of the volume is d by dt of the right-hand side. That's 1/3 pi r squared over h squared, h cubed. Okay, the left-hand side's easy. That's just dv by dt. And the right-hand side, that's going to be pi r squared over h squared times little h squared. But again, the chain rule, because this h isn't a constant, it's actually h of t. So this is times dh by dt. And that is using the chain rule. Okay, since it's h of t, we need to use the chain rule for that. Now, what we want is to solve for dh by dt, and we can get rid of the dv by dt, or we can substitute, because we know that the rate of change of the volume is 1 centimeter cubed per second. So that is our dv by dt is -1. H squared over capital H squared dh by dt. Okay, now we can finally solve for dh by dt. So dh by dt, taking that fraction over to the other side, minus h squared over pi r squared log h squared. Okay, then what we can do is plot this. So the h squared pi r squared, those are all constants. So we can say that this is proportionate to minus 1 over h squared. We can plot this and see how does the rate of change with the height. So as the height decreases, what happens to the rate of change of the height? So we can plot this relationship. Okay, or you can just substitute some values. So maybe when h is a large value, what do we get? As h gets smaller, what happens to dh by dt? So we can plot this relationship to see what happens to dh by dt as h goes to 0. So this little h, it starts off being capital H, and then over time it goes to 0 as the water goes out, and then we can see how quickly does the height change. Okay, so I will leave that for homework. So plot this or just put in some values for this cone. You can come up with your own shape, and then you can see how this changes. So I will put that for homework. Okay. So I think we're going to leave it at that for this lecture. So next time we will go through some more examples, but they follow the same idea. So we've got these two variables. We've got these two variables. They depend on each other with some equation, maybe like this, maybe like a volume equation. So we've got V and H. This is how they depend on each other. And what we want is to see how the rates of change depend on each other. So if V and H are from this equation, what about dV by dt and dH by dt? How are those related to each other? Okay, and sometimes we have to do a little bit of extra working, like on the side here, but that's not so bad. We'll see what to do in those cases with the other problems. Okay, so please have a look at exercise 2.8, number 1 through 8, and then number 13. Okay, so that should help you with these problems here. Okay, but I will upload another video going through some more problems if you do get stuck. Okay, and as always, if you have any questions, you can email me, you can email the tutors. Unfortunately, you can't visit me in my office since we are online for this week. Okay, I'm not too sure when we will be going back, so please look out in your email. Maybe you'll get an email from the university, but I will also let you know if I hear anything about that. Okay, and then just a note, when we do get back, we will be having that class test. Okay, so it might be moved if we're not back by the end of this week, but whenever we do get back, we will be having that class test. Okay. Yeah, so if you have any questions, please let me know. Okay, I'll see you next time.